Hello children, see in this video we will be discussing previous questions from the chapter moving charge and magnetic effect of electric currents. A uniform conducting wire of length 12A, total length of the wire is 12A and resistance capital R is wound up as a current carrying coil in the shape of first an equilateral triangle of side A. So the perimeter of this triangle, that will be 3A. Total length is 12A. So how many turns we can make? 4 turns, because see, each turn will be of length 3A. Total length is 12A. So the total number of turns that we can make is 4. Okay, 4 turns. And the magnetic moment will be 4. Yeah, magnetic moment is actually NIA. So 4, then I, then area. Area of the loop is area of the triangle, that is half into base into altitude. Half, base is A and altitude will be root 3A by 2. Okay, here we have 2 into 2 in the denominator, that 4 and this 4 can be cancelled. So we will get root 3I A square. Okay, and in the second case, a square of side A. So the perimeter will be 4A. Total length of the wire is 12A. How many turns we can make? 3 turns. Okay, so 3 turns. And again the magnetic moment is NIA. Number of turns is 3. Okay, then current. Then area of the loop, that is A square. So root 3I A square and 3I A square. Root 3I A square and 3I A square. Next, ionized hydrogen atom and alpha particle with the same momenta enters perpendicular to a constant magnetic field capital B. The ratio of the radii of their paths are with the suffix h, that is the radius of the circular path of the hydrogen, and R alpha, that of the alpha particle. See, this is the expression for the radius of the circular path, R equal to P by QB. Okay, both the particles are having same linear momentum and moving through the same magnetic field. So P is same, B is same. So we can say R proportional to 1 by Q. Okay, so the radius of the ionized hydrogen atom divided by radius of the alpha particle, okay, as it is inversely proportional to charge Q alpha by QH. For the alpha particle, charge is 2 units, and for the ionized hydrogen atom it is only 1 unit. So it must be 2:1. So this must be the correct option. Okay. Now let's see what we have next. A proton and an alpha particle both enter a region of uniform magnetic field capital B, moving at right angles to capital B. If the radius of circular orbits for both the particles is equal and the kinetic energy acquired by proton is 1 mega electron volt, the energy acquired by the alpha particle. See, the radius of the circular path is actually mv by qb, where mv is the linear momentum. Okay, that linear momentum can be expressed in terms of kinetic energy, that is root of 2m into k, where k is the kinetic energy, divided by qb. Now see, here we have 2 particles, both are moving in circles of the same radii. Okay, R is same, capital B is same. Okay, R is same, capital B is same. So we can say K proportional to Q square by M. Okay, so K alpha divided by K of proton, kinetic energy of proton. Okay, that will be, as it is directly proportional to charge. See, charge of the alpha particle by charge of proton whole square, inversely proportional to mass. So mass will come in the reverse order, mass of the particle proton divided by mass of alpha particle. See, charge of the alpha particle is 2 units and charge of the proton is 1 unit. So it will be 2 by 1 whole square. Okay, mass of the proton is 1 unit and mass of the alpha particle is 4 units. So we will get 1, or kinetic energy of the alpha particle is equal to kinetic energy of the proton. So alpha particle kinetic energy must be equal to that of proton, that is 1 mega electron volt. So this must be the correct option. Now let's see what we have next. An alpha particle moves in a circular path of radius 0.83 centimeter in the presence of magnetic field 0.25 Weber per meter square. The wavelength associated with the particle will be, see, radius of the circular path, linear momentum divided by QB. So linear momentum will be P equal to QBR, and de Broglie wavelength lambda equal to h by P. Okay, now see lambda equal to h divided by QBR. H is Planck's constant and we have 6.6 into 10 raised minus 34. And charge, see it being an alpha particle, charge is 2 electronic charges. Okay, charge equal to twice the charge on a proton. Okay, so 2 into 1.6 into 10 raised minus 19. And B we have 0.25 Tesla or 1 by 4, and radius is 0.83 centimeter, means 0.83 into 10 raised to minus 2. Okay, now see we have this 4 and 0.8, that will be 0.2. Okay, 0.2 into 2, that will be 0.4. Okay, 0.4 into 1.6 will be 0.64. Okay, so this will be approximately equal to 0.66 in the denominator, 6.6 in the numerator, 0.66 in the denominator approximately. So we will get 10 in the numerator. Okay, 10 into 10 raised to minus 34, that will be 10 raised to minus 33. Okay, and see in the denominator powers of 10, 10 raised to minus 19 and 10 raised to minus 2, that is 10 raised to minus 21. So 10 raised to minus 33 in the numerator, 10 raised to minus 21 in the denominator. So it will be 10 raised to minus 12 in the numerator, 10 raised to minus 12 meter. Or we can write 0.01 into 10 raised to minus 10 or 0.01 angstroms. Okay, 0.01 angstroms. This must be the correct option. Okay. The magnetic force acting on a charged particle of charge minus 2 microcoulomb in a magnetic field of 2 Tesla acting in the y direction. See, magnetic field is 2 Tesla acting along positive phi direction, means it is 2 j cap, and force F is equal to q v cross b, and the velocity is given as 2 I cap plus 3 j cap into 10 raised to 6. Q is minus 2 microcoulomb, means into 10 raised to minus 6. Then velocity 2 I cap plus 3 j cap into 10 raised to 6. And magnetic field is 2 j cap. Okay. Now this 10 raised to minus 6 and 10 raised to plus 6 will be 1. Okay. 10 raised to 0 means it is 1. Okay. Then we have minus 2 here. Then 2 I cap cross 2 j cap. I cross j is k. So 2 into 2, that will be 4k. Then 3j cross 2j will be 0. So we will have only 4k. So minus 2 into 4k cap means minus 8k cap. So the force will be of magnitude 8 Newton along negative z direction. Okay, 8 Newton along negative z direction. So this must be the correct option. Okay. Now let's see, under the influence of a uniform magnetic field, a charged particle moves with a constant speed v in a circle of radius r. The time period of revolution of the particle will be. See, time period t equals 2 pi m by qb. So the time period is independent of the radius. It is independent of the speed with which the particle is revolving. Okay. Now depends on r and not on v. It is independent of r. It is independent of both V and R. So this must be true. Okay. Depends on both V and R, false. Depends on V, false. Okay. Now let's see what we have next. A particle of mass m and charge capital Q and kinetic energy capital T enters a transverse uniform magnetic field of induction B after 3 seconds. The kinetic energy of the particle will be. See, when a charged particle is projected into a transverse magnetic field, it experiences a force, and that force will be F equals QV cross B, means the force is always perpendicular to velocity. So the power due to that force is 0. Okay, as this force and velocity are always perpendicular, and the displacement at any instant will be directed along the velocity, which in turn perpendicular to force. So at any moment, force and displacement will be perpendicular. Work done will be 0. No change in kinetic energy. So the particle will be definitely moving with a constant kinetic energy. Okay. So after 3 seconds, its kinetic energy will be T only. same as its initial kinetic energy. A beam of electrons passes undeflected through mutually perpendicular electric and magnetic fields. If the electric field is switched off, then only magnetic field will be acting and it is perpendicular to velocity, so the particle will move in a circle. Okay, so it moves in a circular orbit. Okay, a charged particle is moving in a circle of radius capital R with uniform speed small v. The associated magnetic moment mu is given by. See, when a particle is moving in a circle, when a particle is moving in a circle, the current is actually, when you observe this particle moving in a circle, consider these points. See, as this particle passes through these points, okay, say Q. Now the particle will pass through the same point after a period capital T again. The particle will pass again through that point after one more T. What does it mean? In every time capital T, that is the period, the particle will be passing through these points. If you observe any point on this circle, in every capital T, charge Q will be passing. So what would be the time, what would be the current, that is charge per unit time? In every T, charge is Q. So the current will be Q by T, Q by periods. Okay, so the current I is actually Q divided by periods. Period means it is the time for one revolution. As the particle is moving with constant speed, time is actually distance by speeds. Okay, and what is the distance in one revolution? It is 2 pi r. Okay, 2 pi r divided by v. Okay, that v in the denominator will go like this. Okay, it's actually 2 pi r by v, but that by v will go to the numerator. So this is the current. As the particle is revolving in a circle, this is the current and it is equivalent to a circular current loop. And the magnetic moment is current into area of the loop. See, current is qv by 2 pi r, that we have got. Okay, and here the radius is actually, here the radius is actually capital R, that is the given radius. Okay, so radius is capital R. Okay, now magnetic moment is I into pi r square. What is current? qv by 2 pi r into area pi r square. So finally we will get qvr by 2. Okay, qvr by 2. So this must be the correct option. Now in a certain region of space, electric field capital E and magnetic field capital B are perpendicular to each other, and an electron enters in a region perpendicular to the direction of capital B and E, both and moves undeflected. Then the velocity of the electron is, F with the suffix E, that is the force on an electron due to electric field is E into capital E. Okay, and magnetic force E into V into B. Velocity and magnetic field are perpendicular, so V cross B will be simply V into B. Okay, as the particle travels undeflected, these two forces must be equal in magnitude and opposite in direction. So we can equate the magnitudes of these two forces. So EVB, that is equal to E into capital E into capital E. So V will be E by B. So E by B. So this must be the correct option. Okay, now actually here in a region of space, okay, electric field capital E, electron enters. So here we have an electron. Okay, electron, right? Electron. See, here we have a north pole here, south pole here, positive plate here and negative plate here, something like a box. This side is open, this side is also open. Electron is projected like this. So this electron will experience an electric force like this towards the positive plates. And what about the magnetic force? Okay, electric force is directed towards the positive plate, or say upwards. And what about the magnetic force? See, as this electron is moving towards right, okay, current will be in the opposite direction. Okay, current in this direction. Magnetic field, from north to south means magnetic field in this direction. Okay, current, current is in this direction, magnetic field in this direction, then the force must be downwards. See, we have got electric force like this and magnetic force in the opposite direction. So it can go undeflected if these two forces are of equal magnitude, right? So we will get this velocity equal to E divided by B, right? Now a charged particle of charge Q and mass M enters perpendicularly in a magnetic field capital B. Kinetic energy of the particle is capital E. Then frequency of rotation nu equal to QB by 2 pi m. QB by 2 pi m means it is independent of the kinetic energy or velocity. QB by 2 pi m. So this must be the correct option. Okay. Next, a 10 electron volt electron is circulating in a plane at right angles to a uniform field of magnetic induction 10 raised minus 4 Weber per meter square. The orbital radius of the electron is, see, R equals mv by qb. mv is the linear momentum and it can be expressed in terms of kinetic energy as root of 2me. Okay, and m is the mass of the electron. It is 9.1 into 10 raised minus 31 kilogram. And see, then energy, kinetic energy is 10 electron volt. 10 electron volt is equal to 1.6 into 10 raised minus 19 joule divided by Q, charge on what is this electron, 1.6 into 10 raised minus 19. Okay, and magnetic field is 10 raised to minus 4. Okay, now first let us consider the powers of 10. 10 raised to minus 31 and 10 raised to minus 19, that is 10 raised to minus 50. When it is taken out of the square root, it will be 10 raised to minus 25. And in the denominator, we have 10 raised to minus 19 and 10 raised to minus 4. That is 10 raised to minus 23. In the numerator, 10 raised to minus 25. In the denominator, 10 raised to minus 23. So it will be 10 raised to minus 2 that I have written here. Okay. Now see, we have 1.6 in the denominator. When it is taken inside the square root, it will be 1.6 square in the denominator and 1.6 in the numerator. Okay, so that will be, there will be 1.6 inside the square root in the denominator. Okay, what remains here? We have 2, 9.1 and then 10. Okay, now this 2 by 1.6, we will get 0.8 in the denominator. See, if it is 0.81, it's a perfect square. But we have only 0.8. You can approximate it as 0.81. Square root will be 0.9. That I have written here. Now in the numerator, I have 9.1. Take it as 9. Square root is 3. And what is the square root of 10? You must be knowing it. It is 3.16. Most of the times you can cancel it with pi. Okay, but we are following decimal system. So you must be knowing the square root of 10, it is 3.16. So we have 3 into 3, that is 9. If it is 9 by 0.9, it will be 10. But in the numerator, we have a quantity slightly greater than 9. So it will be slightly greater than 10. And we have 11 centimeter here. Okay. A beam of electron is moving with a constant velocity in a region having simultaneous perpendicular electric and magnetic fields of strength 20 volt meter is minus 1 and 0.5 Tesla respectively at right angles to the direction of motion of the electrons. Then the velocity of the electron must be. See, velocity is E by B. And E is 20 SI units, in SI units, and B is 0.5. So it will be 40 meter per second. Okay. Now let's see. An electron enters a region where magnetic field capital B and electric field capital E are mutually perpendicular. Okay, so it can go undeflected. It can go undeflected also. See, it will always move in the direction of B. That is wrong. It can move in the direction of B. It will always move in the direction of E. That's wrong. It can move in the direction of E. Okay, it always possesses circular motion. Need not be, but this is true. It can go undeflected also, right? Now a charge moving with the velocity v in x direction. So velocity is along I cap. Is subjected to a field of magnetic induction in the negative x direction. B is along minus I cap. So the force will be V cross B in times Q. So force is 0 here. Okay, so remain unaffected because the force is 0. Okay. Now a deuteron of kinetic energy 50 kilo electron volt is describing circular orbit of radius 0.5 meter in a plane perpendicular to magnetic field capital B. Kinetic energy of the proton that describes a circular orbit of radius 0.5 meter. Same as deuteron. In the same plane with the same B. Radius is the same, magnetic field induction is the same. Radius of the circular path mv by qb. Numerator linear momentum can be expressed in terms of mass and kinetic energy like this. Okay, so here we have R same, capital B also same. Okay, charge also same because proton and deuteron, right? So we can say M into E, mass into kinetic energy is constant. So E dash by E, okay, that will be equal to M by M dash. M is the mass of deuteron and M dash is the mass of proton. So E dash, the kinetic energy of proton, that is equal to twice the kinetic energy of deuteron. E is 50 kilo electron volt. So E dash 100 kilo electron volt. A uniform magnetic field acts at right angles to the direction of motion of electron. As a result, the electron moves in a circular path of radius 2 centimeter. If the speed of the electron is doubled, then the radius of the circular path. R equal to mv by qb. Only the speed is changing. Or only the speed is changed. Okay, speed we have made twice. So the radius of the circular path also becomes twice. Earlier it was 2 centimeter. So now it must be twice or 4 centimeter. Okay. A very long conductive wire is bent in a semicircular shape from A to B as shown in figure. The magnetic field at a point capital P for steady current configuration is given by. Okay. See, to find the direction of the magnetic field due to a straight conductor, we have to hold the conductor in the right hands with the thumb along the direction of electric currents. Okay. Now consider this conductor. Hold the conductor in the right hands. Okay, with the current thumb along the direction of current. So we have to hold the upper conductor like this. So the magnetic field due to this upper conductor at P will be along the invert normal. Okay, that field is being represented by cross along the invert normal. It is due to a semi-infinite line. See, if it is going to infinity on both sides, field will be mu 0 I by 2 pi r. But if it is semi-infinite, means one n here and the other n goes to infinity, then the field will be half of the field due to infinite line. That is mu 0 I divided by 4 pi r. Okay, along the invert normal. Now we have this semicircle. Okay, again we have to find out the direction by using the right hand rule. Curl the fingers along the direction of electric current. Field is outwards. So mu 0 I divided by 2r, field due to full circle. Here we have only semicircle. So mu 0 I divided by 4r. Okay, that is directed along the outward normal, so represented by dots. Now again we have one more semi-infinite. Okay, the current is like this. So at point capital P it will be again along the invert normal. So mu 0 I by 4 pi r along the invert normal. Okay. Now see, we have we have to find the sum of these three. Okay. Now if you take this actually mu 0 I by 4 pi r, mu 0 I by 4 pi r, same direction, no? So it will be mu 0 I by 2 pi r. And here we have mu 0 I divided by 4 r. Okay, so in the denominator here we have 4 and here we will have 2 pi. 2 pi means 2 into 3.14. Means 6.28. Here we have only 4. So this is stronger. So the resultant field intensity will be mu 0 I by 4r, mu 0 I by 4r minus mu 0 I by 2 pi r. Okay, this is more compared to this one. Okay, so if you take mu 0 I by 4r, what remains here? 1, what remains here? 2 by pi. Okay, and it will be along the outward normal. Okay, so mu 0 I by 4r, 1 minus 2 by pi, pointed away from the page. Okay. Now the magnetic field on the axis of a circular loop of radius 100 centimeter carrying a current root 2 ampere at a point 1 meter away from the center of the loop is given by. See, this is the expression for the magnetic induction at a distance x from the center of a loop of radius a carrying a current I. Okay, A is the radius, I is the current, x is the distance of the point of observation from the center of the loop along its axis. Here x is 1 meter and A is 100 centimeter, both are same, each equal to 1 meter, x equal to A equal to 1 meter. So let's find B. Mu 0 is 4 pi into 10 raised to minus 7. A is 1 meter, so A square will be 1. Okay, current is root 2, right? And in the denominator we will have 2. Then 1 plus 1, that is 2 raised to 3 by 2, that is 2 raised to 3 by 2. Okay, now this root 2, this 2 raised to 3 by 2 is actually 2 root 2. Root 2 and root 2 can be cancelled. So in the denominator we will have 2 into 2, that is 4, and 4 can be cancelled. So it will be pi into 10 raised to minus 7 or 3.14 into 10 raised to minus 7 Tesla. So this must be the correct option. A closely packed coil having 1000 turns has an average radius of 62.8 centimeter. If current carried by the coil is 1 ampere, the value of magnetic field produced at the center of the coil will be B equal to mu 0 Ni by 2R if there are n turns. Mu 0 is 4 pi into 10 raised to minus 7 and number of turns is thousands. Okay, current will be 1 ampere and in the denominator we have 2R. 2 radius is 62.8 centimeter, can be converted into meter by multiplying 10 raised to minus 2. Okay, this is actually 62.8 is actually 20 pi, right? Into 2, that is 40 pi. 40 pi. 4 pi and 40 pi in the denominator, that will be 10. 10 into 10 raised to minus 2 is actually 10 raised to minus 1. When it is taken to the numerator, it will be 10 raised to plus 1. Already there is 10 raised to 3. And 10 raised to 1 will give you 10 raised to 4 into 10 raised to minus 7 will give you 10 raised to minus 3. Okay, so we have 10 raised to minus 3 Tesla. So this must be the correct option. Okay, a long solenoid of radius 1 millimeter has 100 turns per millimeter. 100 turns per millimeter. See, in every millimeter 100 turns. So in 1000 millimeter or in 1 meter, 100 into 1000, that is 10 raised to 5 turns per meter. Okay, that is in SI units. Okay, if 1 ampere current passes through the solenoid, the magnetic field strength at the center B equal to mu 0 Ni, and mu 0 is 4 pi into 10 raised to minus 7. Number of turns is 10 raised to 5 and current is 1 ampere. This is 4 pi, that is 12.56 into 10 raised to minus 2. Okay, 12.56 into 10 raised to minus 2 Tesla, this one. Okay. A thick current carrying cable of radius capital R carries current I uniformly distributed across its cross section. Variation of magnetic field B of R due to the cable with the distance R from the axis of the cable is represented by B equals mu 0 IR by 2 pi R square. Inside the cable it varies linearly with the distance R and outside it varies with the 1 by R. So this must be the graph. Okay, a long solenoid 50 centimeter length having 100 turns carries a current of 2.5 ampere. The magnetic field at the center of the solenoid is, see, 200 turns per, see, actually 50 centimeter length have 100 turns. 50 centimeter means half meter. In half meter 100 turns. So in 1 meter 200 turns. So 200 turns per meter, that is number of turns per unit length. B is mu 0 Ni. Mu 0 we have 4 pi into 10 raised minus 7. Number of turns per unit length is 200 and current is 2.5. Okay. Now see, we will have this 2.5 into 200. That will be 500. It can be expressed as 1000 divided by 2. Okay. By 2 into 4 pi will be 2 pi. Then 1000 into 10 raised to minus 7. That will be 10 raised minus 4. Now this 2 pi can be expressed as 6.28 into 10 raised minus 4 Tesla. 6.28 into 10 raised to minus 4 Tesla. Okay. Two toroids, 1 and 2 have total number of turns 200 and 100 turns with average radii. See, toroid means a solenoid in circular shape. Okay, means this is a toroid. Why average radius? Now suppose, see, this is 20 centimeter. Okay, and this is say 21 centimeter. Radius is not constant. Okay, or see, it may have inner radius and outer radius for a toroid. That is why the average radius is given. Okay, now magnetic field mu 0 Ni, where small n is the number of turns per unit length, that is total number of turns divided by length, that is equal to 2 pi into average radius. Okay, we have got two toroids. See, when we consider these two toroids, number of turns are different. Then radii are also different. Okay, all other factors are same for both the toroids. So we can say B proportional to n by R. So B1 by B2 will be N1 by N2 times R2 by R1. N1 by N2 is 200 by 100 and R2 by R1 will be 20 by 40. So this we will get 1, or the ratio must be 1:1. Okay. Now let's see, an electron moving in a circular orbit of radius R makes n rotations per second. Okay, so current is actually E by T, where T is the period, 1 by T is the frequency. So the current will be NE. Magnetic induction at the center is mu 0 I by 2R if it is considered as equivalent to a current loop. So it will be mu 0 Ne by 2R. Mu 0 Ne divided by 2R. When a proton is released from rest in a room, initially it is at rest. So there won't be any magnetic force, even if there is a magnetic field. Okay, it starts with an initial acceleration A0. So that is only due to the electric fields. So what would be the electric force? MA0. Okay, initial acceleration, even though it is at rest, okay, it experiences an acceleration, means that acceleration is only due to electric force. The acceleration is A0, so the force will be MA0. Okay, electric force is MA0 equal to electronic charge into intensity of electric fields. Okay, now it being a proton, positively charged particle, then it will experience a force along the direction of the electric field. If it experiences a force due west, then electric field must be directed due west. Okay, and it is equal to MA0 by E due west. MA0 by E due west. See, we have only two options in which this first electric field intensity is correct. MA0 by E west, then MA0 by E west. So we can rule out these options B and C. The correct option will be either 1 or D, either A or D, right? Now, when it is projected towards north with a speed V0, it moves with an initial acceleration 3A0 towards west. See, it experiences an acceleration 3A0 towards west, of which A0 is due to electric field. So the remaining 2A0 will be due to magnetic fields. See, when it is projected with velocity V0, it experiences an acceleration 3A0 due west, of which A0 is due to electric field. So the acceleration due to magnetic force will be 2A0. So the magnetic force will be M into 2A0. Okay, magnetic force M into 2A0. It must be EVB. Okay, so EV0B. Okay, so the magnetic field is 2MA0 divided by EV0, and we have to find the direction of the magnetic fields. Okay, now let's see, when it is projected towards north, suppose this is north, so this will be south, this will be east, and this will be west. We have to use the Fleming's left hand rule. As the particle is projected due north, current will be due north, this one. Okay, force is due west. Okay, force should be like this. Current is due north, force is due west, then the magnetic field is downwards. Okay, current is due north, force is due west, so the magnetic field should be directed downwards. Okay, so it must be 2ma0 by ev0 down. 2ma0 by ev0 down. So this must be the correct option. Now two similar coils of radii are lying concentrically with their planes at right angles to each other. The current in the are I and 2I respectively. The resultant magnetic field induction at the center will be. See this one. Okay, see it carries a current like this. So the magnetic field will be like this. B1. So B1 will be mu 0 I divided by 2R. Okay, and the second one. Okay, second one, see the current is like this. Current is like this. So the field will be along this direction. Mu 0 2I by 2R. Mu 0 2I by 2R. Okay, these two magnetic fields are perpendicular to each other. So the resultant field will be under root b1 square plus b2 square. Common factor you can take outside. Mu 0 I by 2R. So here what remains 1. Here what remains 2. So under root 1 square plus 2 square, that will be root 5. Mu 0 I divided by 2R into root 5. Okay. Now mu 0 I by 2R into root 5. Okay. Charge small q is uniformly spread on a thin ring of radius capital R. The ring rotates about its axis with uniform frequency f. So the current associated with it will be q by t or qf. Okay, qf. The magnitude of induction at the center of the ring, B equal to mu 0 I by 2R. Okay, mu 0 qf divided by 2R. Mu 0 qf divided by 2R, this one. A current loop consists of two identical semicircular parts, each of radius r, one lying in the xy plane. One lying in the xy plane. Okay, so this one xy plane. Magnetic field will be along the z direction. So mu 0 I by 4r k cap. Okay, so mu 0 I by 4r k cap. And the second one is in zx plane. Okay, second one is in zx plane. So current is like this and the magnetic field will be along positive y direction. Mu 0 I by 4r j cap. Mu 0 I by 4r j cap. So it will be mu 0 I by 4r into root 2. Or we can write mu 0 I by 2 root 2r. Mu 0 I by 2 root 2r. This must be the correct option. Okay. Now two circular coils 1 and 2 are made from the same wire, but the radii of the first coil is twice that of the second. What potential difference in volts should be applied across them so that the magnetic field at their centers is the same? This R1 radius of the first coil is twice the radius of the second. Magnetic field B equal to mu 0 I by 2R. Okay. Now see B equals mu 0 I by 2R. Let me multiply both the numerator and denominator by 2 pi r lambda. 2 pi r lambda. Okay. 2 pi r is the length of one turn and lambda is the resistance per unit length. Okay. Resistance per unit length. Okay. Now see 2 pi r, that is the length into lambda resistance per unit length. So 2 pi r lambda is the resistance of the turn into current I, that will be the voltage. So mu 0 voltage V divided by in the denominator there will be 4 pi r square lambda. So the magnetic field, okay, at the center will be mu 0 V divided by 4 pi r square lambda, or let us say B, or let us say B is the same, so here we have V proportional to r square. Two circular coils 1 and 2 made from the same wire, but their radii of the first coil is twice that of the second. What potential difference in volts should be applied across them so that magnetic field at the centers is the same? The difference is only in voltage and radius. All other factors are same. See, lambda being the resistance per unit length is same for both the circular coils because they are made from the same wire. Okay, so we will get V proportional to R square. So V1 by V2, R1 by R2 whole square. R1 equal to 2R2. So we will get 4. Okay, so V1 by V2 equal to 4. Now let's see what we have next. A long solenoid carrying a current produces a magnetic field B along its axis. If the current is doubled and the number of turns per centimeter, means number of turns per unit length is halved, the new value of the magnetic induction, B equal to mu 0 Ni. And B dash, mu 0 is same as before, no change. But number of turns per unit length is halved, so N becomes N by 2. And current is doubled, I is to be replaced by 2I. So we will get again mu 0 Ni or B dash equal to B. Okay, so this is the correct option. Now let's see, a wire carries a current. Maintaining the same current is bent first to form a circular plane coil of one turn, which produces a magnetic field B at the center of the coil. The same length is now bent more sharply to give a double loop of smaller radius. Okay, using the same length of wire. The magnetic field at the center of the double loop caused by the same current is. See, magnetic field at the center B equal to mu 0 by R 2R into number of turns. Okay. Now let me multiply both the numerator and denominator by N pi. Okay, N pi. See, here I have 2R. Now denominator is multiplied by N pi. So numerator also to be multiplied by N pi. Already there is N. So it will become N square. Okay, then mu 0 I pi. See, 2 pi r is the length of each turn into capital N number of turns. That will give you the total length of the wire. Okay, let it be small l. Okay, so pi mu 0 I divided by L into N square. Here we have got two coils. The total length of the wire in both the coils are the same. So L is same, mu 0 is same, pi is same. Both carry the same current. I is also same. So magnetic field at the center proportional to N square. So B dash by B equals N dash by N whole square. N is 1, N dash is 2. So 2 by 1, 2 square is 4. So B dash will be 4B, right? 4B. This one. Okay. Two long parallel wires P and Q are both perpendicular to the plane of the paper with a distance 5 meter between them. If P and Q carry current 2.5 ampere and 5 ampere respectively in the same direction, means here there is a conductor passing like this. See, current is into the plane of the board. It is being represented by cross, current into the plane of the board, and it is 2.5 ampere. There is another parallel conductor at a distance 5 meter from it, okay, along the same direction, and it also carries a current in the same direction, but it is 5 ampere. Okay, we have to find the resultant intensity at the midpoint of the line joining them. Means at a distance 2.5 meter from both the conductors in between them. Okay. Now see, as this conductor carries a current like this, the magnetic field due to this conductor at the point of observation will be like this, means B1 like this. Now magnetic field due to this conductor, on the right side of it downwards and on the left side of it upwards. Field due to the first conductor is downwards and it is due to a current of 2.5 ampere. Field due to the second conductor is upwards, but it is due to a current of 5 ampere. So the field at the point of observation due to the second conductor is stronger. So it is being represented by a longer line. Okay. So the resultant magnetic field intensity will be B2 minus B1. Okay. So mu 0 I2 by 2 pi r minus mu 0 I1 by 2 pi r equals 2.5 meter. So mu 0 I by 2 pi r I2 minus I1. Mu 0 divided by 2 pi r, distance is 2.5 meter, and I2 minus I1 5 minus 2.5. This 2.5 and this 2.5 can be cancelled. Mu 0 is 4 pi into 10 raised minus 7 divided by 2 pi. Okay, so it will be mu 0 by 2 pi. Okay, mu 0 divided by 2 pi. Magnetic field intensity at the center of a coil of 50 turns, radius 0.5 meter and carrying a current of 2 ampere is mu 0 Ni by 2R, that is the field at the center. 4 pi into 10 raised to minus 7, the value of mu 0, number of turns is 50, current is 2 ampere. Okay, yes. And 2, radius is 0.5 meter. In the denominator, 2 into 0.5, that is 1. Okay, numerator 50 into 2, that is 100 into 10 raised to minus 7, that will be 10 raised to minus 5. then 4 pi, that will be 12.5 into 10 raised minus 5, or 1.25 into 10 raised minus 4, 1.25 into 10 raised minus 4, right? Next, see, if a long hollow copper wire carries a current, magnetic field is produced only outside. See, inside the hollow pipe, magnetic field is 0. Okay, and outside it varies as 1 by r, mu 0 I by 2 pi r. Okay, so field outside the pipe only, outside the pipe only. Now let's see the magnetic induction at a point capital P, which is at a distance of 4 centimeter from a long current carrying wire is 10 raised to minus 3 Tesla. The field of induction at a distance 12 centimeter. Earlier it was 4, now it is 12. Means the distance is made 3 times. Okay, magnetic field be proportional to 1 by r. When the distance is made 3 times, field will become 1/3. See, 1 into 10 raised minus 3 by 3. So it is 3.33 into 10 raised minus 4. Okay, 3.33 into 10 raised minus 4. A wire carrying current I along the positive x has length L. So the current element is directed along the positive x direction or I cap. Okay, so IL, current element IL will be IL I cap. Okay, the magnetic field is given as 2I plus 3J minus 4K cap. Okay, so F is IL cross B. Okay, IL, then I cross I is 0. And I cross J will be K. So 3K. And I cross K will be minus J. Okay, see, I cross K is minus J. So I cross minus K will be plus J. So we will get 4J cap. Right? Here we have IL 3K cap plus 4J cap. This 3K cap and 4J cap being perpendicular, its magnitude will be under root 3 square plus 4 square. Okay, so it must be 5 IL. Okay, here this L must be capital letter L, right? Okay, now let's see what we have next. Two very long straight parallel conductors A and B carry a current of 5 ampere and 10 ampere respectively and are at distance of 10 centimeter from each other. The direction of current in the two conductors are the same, so there will be force of attraction between them if they carry current along the same direction. Okay, what is the force per unit length? It is mu 0 I1 I2 divided by 2 pi r. Mu 0 is 4 pi into 10 raised minus 7. I1 and I2 5 and 10. Okay, 2 pi r is 0.1 meter. Okay, so this will be 4 pi by 2 pi, that is 2, into 5, 10 into 10, 100 by 0.1, that is 1000, into 10 raised to minus 7, that is 10 raised minus 4 Newton attractive. 1 into 10 raised to minus 4 Newton per meter attractive. Okay. Now a 250 turn rectangular coil of 2.1 centimeter length, 1.25 centimeter width carries a current of 85 microampere and is subjected to a magnetic field of strength 0.85 Tesla. Work done for rotating the coil by 180 degree. Initially, angle made by the coil or the dipole moments normal to the coil with the direction of the magnetic field is 0, and finally it is 180. See, the work done is MB cos theta 1 minus cos theta 2, where capital M, the dipole moment, is NIA. Okay, now number of turns, that is 250, it can be expressed as 1000 by 4, 10 raised to 3 by 4. Current is 85 microampere, 85 into 10 raised to minus 6. Area is 2.1 centimeter length and 1.25 centimeter breadth. Okay, this centimeter can be converted into meter by 10 raised minus 2, again 10 raised minus 2, so it will be 10 raised minus 4. Okay, then this 1.85 Tesla, then cos 0 minus cos 180. Okay, now cos 0 is 1, cos 180 is minus 1. 1 minus minus 1, that is 2 into 0.85, that is 1.7. Okay, now see, we have this, okay, this 8.5, no, this 8.5, let me write it as, see, 0.85, okay, 0.85 into 10, right, that 10 and 10 raised to 3, that is 10 raised to 4, Okay, 10 raised to 4 and 10 raised to minus 4 can be cancelled. Okay. Now see, this cos 0 is 1, cos 180 is minus 1, 1 minus minus 1 that is 2 into 0.85 that is 1.7. Okay, here we have 85. It can be written as 8.5 into 10. Let me write that 8.5 here. Then 10 into 10 raised to 3 that is 10 raised to 4 and this 10 raised to minus 4 that will be 1. Okay. Then what remains? 10 raised to minus 6 and in the denominator we will have 4. This 2.5 I have written here 1.25 also. Okay. Now see this 0.85. Okay. 0.85 we can write it as see 1.7 into 5. This 8.5 can be written as 1.7 into 5. See, square of 17 is 289. So 1.7 square will be 2.89. Okay, let me write or split this as 1.7 into 5. 1.7 into 1.7, 2.89. Okay, 5 will be remaining that I have written here. 10 raised to minus 6, then 2.1 and 1.25. Okay, now here we have 4 in the denominator. Okay, this 4 and 1.2. 1.25 approximately 0.3. Okay, now see we have this 5 and 2 that is 10. 10 into this 0.3 that will be 3 and this is also approximately 2.893. 3 into 3 will be 9. Okay, into 10 raised minus 6. So 9 into 10 raised minus 6 means 9 microjoule approximately. Okay, now let's see an arrangement of 3 parallel straight wires placed perpendicular to plane of paper means this conductor carries a current like this. Okay, this conductor also carries a current like this. This also carries a current like this. Okay, same current I along the same direction all along the outward normal. Okay, magnitude of force per unit length on the middle wire B is given by. Okay, due to this first conductor A, as it carries a current like this, magnetic field at the position of B will be like this. See, this is the field. So the magnetic field at this position due to conductor A will be like this. B with the suffix A. Now consider this C. Okay, as it carries a current like this, the magnetic field due to this will be like this. So due to the conductor C, magnetic field here will be directed down. Okay, this B with the suffix A and B with the suffix C, the intensity of magnetic field due to the conductors A and C are of equal magnitudes. Each equal to mu 0 I divided by 2 pi d. Okay, mu 0 I divided by 2 pi d. Now these two fields are perpendicular to each other. So the resultant magnetic field intensity will be B root 2. Okay, so B root 2 and B equals mu 0 I by 2 pi d. Okay, now we have to find the force per unit length of the conductor. See this middle conductor. Okay, BIL. Okay, resultant field is B root 2 I, L is 1. Okay, this is B root 2 and I. So mu 0 I square. Okay, then root 2 by 2, there will be root 2 in the denominator. Mu 0 I square root 2 pi d. Mu 0 root 2 mu 0 I square by pi d. This one. Okay. Now a rectangular coil of length 0.12 meter and width 0.1 meter having 50 turns of wire is suspended vertically in a uniform magnetic field of strength 0.2 Weber per meter square. Coil carries a current of 2 ampere. So it will act as a dipole of moment M equal to NIA. 50 turns, current is 2 ampere. Okay, area will be length into breadth 0.12 into 0.1. Okay. So this will be, this is 50 into 200. Okay, so 1.2 into 1. So it will be 1.2 ampere meter square. Okay, now torque will be M cross B or MB sin theta. So M is 1.2 into 0.2 then root 3 divided by 2. Okay, now see 1.2 divided by 2 that is 0.6 into root 3 is 1.732. 0.6 into 1.732 will be approximately 1. Okay, into 0.2, so it will be 0.2 Newton meter. Okay, 0.2 Newton meter approximately. Okay. Now let's see a current loop in a magnetic field. Current loop is a magnetic dipole. See, when it is kept in a magnetic field, it can be equilibrium in two positions. When the dipole is parallel to the field, that equilibrium is stable. When the dipole is anti-parallel to the field, then also in equilibrium, but it is unstable. Okay, see, magnetic field and dipole moments. Okay, angle theta 0. Okay, theta 0, torque mb sin theta, that is 0, equilibrium is stable. This is the direction of the magnetic field and this is the direction of the dipole moment. Angle between these two vectors is 180 degree. Then also torque equal to 0, but the equilibrium is unstable. Can be equilibrium in two orientations, one stable while the other is unstable. This must be the correct option, C. Okay, now let's see. A closely wound solenoid, 2000 turns and area of cross section 1.5 into 10 raised minus 4 meter square, carries a current of 2 ampere. It is suspended through its center and perpendicular to its length, allowing it to turn in a horizontal plane in a uniform magnetic field of 5 into 10 raised minus 2 Tesla, making an angle of 30 degree with the axis of the solenoid torque. See, capital M, the dipole moment is NIA. Total number of turns 2000. Current is 2 ampere. Area is 1.5 into 10 raised minus 4. Okay, this 2 into 1.5, that is 3 into 2000. 6000 into 10 raised minus 4, that is 0.6. Torque will be mb sin theta. Dipole moment is 0.6. B is 5 into 10 raised minus 2. Sin theta is sin 30. Okay, sin 30 is 1 by 2 into 0.6, that is 0.3 into 5, that is 1.5 into 10 raised minus 2. 1.5 into 10 raised to minus 2 Newton meter. Okay. Now a particle having charge q moves with velocity v through a region in which both an electric field capital E and a magnetic field capital B are present. The force on the particle is, electric force is QE and magnetic force is QV cross B. So this will be the resultant force. Okay. A long parallel, two long parallel wires are at distance 1 meter. Both of them carry 1 ampere of current. The force of attraction per unit length. That is actually the definition of ampere. It is force per unit length 2 into 10 raised minus 7 Newton per meter. This one. Okay. See, a straight wire of length of 0.5 meter carrying a current of 1.2 ampere is placed in a uniform magnetic field of 2 Tesla. The magnetic field is perpendicular to the length of the wire. The force on it will be IL cross B. So ILB sin 90. Okay, theta is 90 here. So it will be BIL. Magnetic field intensity is 2 Tesla. Current is 1.2 ampere. And length is 0.5 meter or 1 by 2 meter. So this will be 1.2 Newton. 1.2 Newton. Okay. A circuit contains an ammeter, a battery of 30 volt and a resistance of 40.8 ohm, all connected in series. If the ammeter has a coil of resistance 480 ohm and a shunt of 20 ohm, the reading in the ammeter will be. See, here we have 480 ohm and here this is 20 ohm. This 20 ohm can be considered as 480 by 24. What do you understand by 480 by 24? See, when you connect two identical resistors, each equal to R in parallel, effective will be R by 2. When 3 are connected in parallel, R by 3. When 5 are connected in parallel, it is R by 5. When 24 identical resistors, each equal to 480, are connected in parallel, it will be 480 by 24. That is equal to 20. So this 20 ohm can be considered as the parallel combination of 24 identical resistors, each equal to 480. And here we have one more 480 connected parallel to it. So altogether 25 identical resistors, each equal to 480, are connected in parallel. So here the total will be 480 divided by 25. 480 by 25. That you will get 19.2. Here we have 19.2, here we have 40.8. Total will be 60. And the current drawn from 30 volt cell will be 30 by 60, that is equal to 0.5 ampere. This one. Okay. Now an ammeter, 0.2% of main current passes through the galvanometer. If resistance of the galvanometer is G, the resistance of the ammeter will be. See, here is galvanometer and here is the shunt. Only 0.2% passes through galvanometer. remaining 99.8 will be passing through the shunt. Okay, and here we have shunt, it is S into current through it 99.8. Okay, resistance into current, that is the voltage across the shunt. That will be equal to the voltage across the galvanometer because they are connected in parallel. When two elements are connected in parallel, voltage across them will be same. How do you find the voltage? Resistance into current. Here the current is 0.2, resistance is G. Here the current is 99.8, resistance is S. So you will get S equal to 0.2 G by 99.8 or 2G by 998 or G by 499. Okay, so this is G by 499. As I have told you earlier, it is equivalent to G like that. 499 identical resistors, each equal to G, connected in parallel. So here we have 499 G connected in parallel, and it is connected in parallel to another G. So altogether 500 identical resistors equal to G are connected in parallel. So it will be G by 500. Okay, this will be the effective resistance. A galvanometer has a coil of resistance 100 ohm and gives a full scale deflection for 30 milliampere current. It is to work as a voltmeter 30 volt range. The resistance required to be added, Vg, full scale deflection voltage, that is G into Ig, means 100 into 30 into 10 raised minus 3, that is 3 volt. Initial full scale deflection voltage is 3. It is to be converted into measure a maximum voltage of 30 volt. Means the voltage capacity is to be increased by a factor of 30 by 3, that is 10. Required high resistance to be connected in series, that is N minus 1 into G. Children, if we want to increase the current capacity by N times, a small resistance is to be connected in parallel. It's called shunt and it is G by N minus 1. If you want to increase the voltage capacity by N times, a high resistance is to be connected in series. It's called multiplier. Okay, and it is N minus 1 into G. Okay, here we have N equal to 10. So the required high resistance to be connected in series, that is N minus 1 into G means 10 minus 1, 9 into G is 100. 9 into 100, 900. Okay, so 900 ohm, right? Okay, now let's see. A galvanometer having a coil resistance of 60 ohm shows full scale deflection when a current of 1 ampere passes through it. It can be converted into an ammeter to read up to 5 ampere. Okay, now see N equal to I by Ig. Full scale deflection current is 1. It is to be converted into an ammeter capable of measuring 5 ampere. So N is I by Ig, that is 5. And shunt is G by N minus 1. Okay, 5 minus 1, that is 4. 60 by 4, 15 ohm. Okay, so putting in parallel a resistance of 15 ohm. Okay, next a galvanometer of resistance 50 ohm is connected to a battery of 3 volt along with a resistance of 2950 ohm in series. Okay, a full scale deflection of 30 divisions is obtained in the galvanometer. Okay, in order to reduce this deflection to 20 divisions, okay, now the full scale deflection is Vg. When its range is improved, that Vg will be 20 divisions. So full scale 30 divisions will be V equal to, see, 20 divisions Vg, so 1 division Vg by 20 and 30 division Vg by 20 into 30, that is 1.5 Vg. Originally it was Vg. Now it is 1.5 Vg. So the voltage capacity is increased by 1.5 times. So the required high resistance in series will be N minus 1 into G. Originally 50 plus 2950, that is 3000. Now the required high resistance is N minus 1 into G means 0.5 into 3000, that is 1500. Total resistance will be 3000 plus 1500, that is 4500, in which the galvanometer is only 50. So the remaining will be 4450. Okay, 4450. right? To convert a galvanometer into an ammeter, one needs to connect a low resistance in parallel. Low resistance in parallel. Okay, children, we have discussed all the questions from this chapter that appeared for NEET and earlier for APMT. See, you need to expect only this type, this level, or questions of this much difficulty only. Okay, thank you.